Okay, so I'll just show that to you. I could show you the previous video. So if you look at here, so rubidium here, so the noble gas just before rubidium here is going to be krypton. Okay, so when I'm writing the electronic configuration of rubidium, I'm going to write krypton. So krypton is already representing 36 electron. So rubidium is now 37 electron. Okay, so then it's going to be so you see this is the period number. If you remember these numbers, they are the period numbers, and these one, they are the group numbers. Okay, so the group number shows how many valence electron there is, so outermost electron, and the period number actually shows how many shells there are. So rubidium is in period 5, so then I would say 5s1. Okay, so let's say I want to write for let's say barium. Okay, so I look at the noble gas that is just before barium, so it's xenon here. So when I would write for barium, so that's for RB. So for barium, it would be xenon, which is already representing 54 electrons. And then for barium, it would be, so it's period 6, so 6s2. So this is 54, 55, 56. Okay, so this is how you can use this kind of notation to write the electronic configuration of any element actually. Okay, we're going to see in more details about this at the end of that unit. Okay, for now on, that should be just fine. Now, electronic configuration of D block elements now. So this is called S block. Why S block? Because if you look at here, so here you see we're filling in the s orbitals. So everything that is in here will be filling in just s orbitals. The last shell that we fill in is the s orbital. That's why this is called the S block. Then this is called the P block, because the last shell that we fill in for these elements is the p orbital, the p subshell. Okay, and here it's called the D block, because what we will be filling in at the end is the D subshell. Okay, so S, P, and D blocks. So they are called D block as electrons are filled in the D subshells. So it's the last subshells that we're going to fill is the D subshell. So first row consists of elements from scandium to zinc. Okay. Now let's see for the D block elements how we're going to fill in. So scandium, 21 electrons. So 1s2, 2s2. I'm going to write for everything. I'm not doing I'm not using AR for now. I'm just going to write for everything, and then later on you can use AR. So 1s2, 2s2, 2p6, 3s2, 3p6, and then we fill 4s2. So that's 20 now. So then the 21st is going to go in the D subshell. So 3d1. Remember, we're going to 3d1 because of the order from Aufbau's principle. Okay, go back to that order of filling in electrons. So 3d1. Here I'm not showing all the previous boxes, so I'm just showing for 3D and 4s. So 4s2 completely filled, and then 3d1, so there's 1 electron. Okay, titanium, So again, 1s2, you're going to write that again, 1s2, 2s2, 2p6, 3s2, 3p6. So then again, you're going to have 4s2 and then 3d2. Now, I'm going to use AR to make it easier. So AR is 18, so 19, 20, and then 3d2, 22. So 4s2 and 3d2. Okay, now when I'm drawing the electron in box diagrams for the outer orbitals, when I'm drawing it, I'm going to draw it in order of the energy levels. But when I'm writing the electronic configuration, I'm going to write it in order of the Aufbau principle. Okay. When I'm filling in, actually I'm filling in according to the Aufbau principle, but when writing it, actually you should write it in order of the energy levels. So this is good, this is okay, but when I'm going to write it properly, so I would write AR, so 3d2 and 4s2. That's how I'm going to write it. But when I'm filling in, I will fill in the 4s first, and then I will fill in the 3d. Let's try for vanadium. So AR, so that's 18. Okay, 18. Then, so 3d, 4s. But when I fill the 4s first. So 18, 19, 20, and then 3 here. So then I'm going to have 1, 2, and then 1, 2, 3. Chromium, so 18, 3d, 4s. I fill in the 4s first, and then I fill the 3d, so 3d, 4. So here, 1, 2, 3, 4. Manganese, AR, 18, 4s, 3d, 2, 5. 2, 3, 4, 5. Okay. So you see that everything is completely, it's half filled here. So this will have extra stability. So AR, 4s and 3d, 18, 19, 20, 26. So I'm going to have 6 here. 1, 2, 3, 4, 5, and then 6. Okay, you can fill up for the others and then come back to it. Please check it again, because there's going to be an exception that I'm going to talk about. We're going to go back for all of this. So just pause the video, complete all of this, and then you can check. Okay, this is what you should have if you fill in everything. Now, be careful now. Remember that we said that half filled or completely filled subshells have extra stability. So we haven't applied this actually. Look at chromium. Look at this configuration. So this has 4 electrons here. This is nearly stable. If there would be 1 electron over here, it would be stable. So what happens actually? There's actually a jump of the electron. So 1 electron is going to jump over here, so that we end up with something like that. Okay, so it jumps. Why does it jump? Because it wants to have an electronic configuration that is half filled or completely filled, so that it becomes stable. Okay, so electrons shift from 4s to 3d as half-filled orbital is more stable. Okay, so let's see what will happen here. So this is not 5 anymore. This is not 4 anymore, and this is not 2 anymore. So that's going to be 3d5 4s1. So this is an exception. Okay, be careful. Second exception you will see for copper here. So again, the same thing. This is almost stable. Everything here is filled. Almost stable. If this would be completely filled, it would be stable. So what happens? So this is going to jump and is going to go in here. Okay, so there's a jump from the 4s to the 3d. So then it's not d9. So it's going to be d10 4s1. So chromium and copper are the exceptions. You have to be careful. This is the correct electronic configuration state. This is the correct electronic configuration state. So what happens? So electrons are going to shift from 4s to 3d as half filled or completely filled d orbitals are more stable. Okay, so this is very important for you to know. So try to complete for all of this, and then you can check your answer. So pause the video, complete everything, and then you can play the video again to check your answers. So that should be your answer. And see all of these elements here, they are in the P block. So we're filling in the P subshell. Okay, so P block, so everything here that's completely filled. Okay, now when I'm filling in, I'm going to fill the 4s first, then the 3d, then the 4p. Okay, be careful the order of filling in. And like I explained, so rubidium 37. Now we're going to move to the next noble gas. So here, so this is what we have been filling in. Okay, so because we were filling in this, we were using argon as the reference for this. So 18 electrons, and we've been adding to it. But when we move to this part now, rubidium, strontium, and everything over here, we would be using now krypton as the reference. Okay, so you always use the halogen that is before the elements in that period. Okay, so these are the P blocks, so that's why we have been filling in the P orbital here. Okay, so that's it for atoms. Now let's see for ions. So if you still remember, atoms will always want to have the electronic configuration state of the nearest noble gas. So to do that, they are going to either lose electrons or gain electrons. So noble gases have stable electronic configuration because the orbitals are completely filled. So these are the noble gases. Write down the electronic configuration for each one of them. So pause the video, write it down, and then you check. So these are the electronic configurations, and you can see so last subshell completely filled, so 2s to p. the energy level is completely filled. Here 2s2p completely filled, 2s2p completely filled. They are all in the p block, so the last orbital that we're filling is the p orbital. Okay, so now atoms will lose or gain electrons to have the electronic configuration of the noble gas, nearest noble gas. So let's look at sodium. So proton 11, electrons 11, electronic configuration 1s2, 2s2, 2p6, and then 3s1. Na plus, it's going to lose one electron, so 10 electrons, so 1s2, 2s2, 2p6. This is the same as neon. Okay, chlorine 17 protons, 17 electrons for the atom, so 1s2, 2s2, 2p6, 3s2, and 3p5. And here negatively charged, so means that it's going to gain one electron, 18 electrons, so 1s2, 2s2, 2p6, 3s2, and 3p6. So it has gained one electron. Here it has lost one electron. Okay, so atoms of metals will lose electrons to form positive ions called cations. Atoms of non-metals will gain electrons to form negative ions called anions. And anions and cations have stable electronic configuration state. So complete for all of them. And so pause the video, complete for all of them, and then you can check your answers. Now if you look at all of these, so check your answers. If you look at all of these, they all have 10 electrons and they all have the same electronic configurations. So ions containing the same number of electrons and having the same electronic configuration are said to be isoelectric. So all of these, they are actually isoelectric. And you will see isoelectricity for everything that, so all the non-metals before and metals after a noble gas. So that's the noble gas. So the elements before and the elements after are going to be of the same electronic configuration. So the ions of these elements will be of the same electronic configuration. So this is what I was saying. So ions of elements found just before and just after a noble gas are isoelectric. So see neon here. So these will have same electronic configuration as neon for their ions, of course. And argon, these three and these two, as well as these, will have the electronic configuration of argon for their ions. Okay, so it's like that. Now, formation of ions by transition elements. Now, when transition elements form cations, because they are metals, so they will lose electrons. Electrons are lost from the outermost 4s orbital first, then from the 3d orbital. Now, when we fill in 4s first, and then we fill in 3d. So when electrons are lost, they are lost from the 4s first and then from the 3d. So let's write for Fe. So that's for Fe. So we fill in 4s first, then we fill in 3d. Now when we're removing electrons, we'll be removing, so there's 2 electrons that are removed, we'll be removing from the outermost 4s orbital. So we'll end up with Ar 3d6 for Fe2 plus. For Fe3 plus, so we remove from the 4s and then we remove from the 3d. So then it would be Ar 3d 5 because we're removing 3 electrons. Now, careful here. So electrons removed from the outermost 4s. Now, if you look at copper, copper is going to have Ar, so 3d5, 4s1. Remember, it's going to have 3d5 because it will want to have a stable electronic configuration with half-filled orbital. So then Cu plus, so 1 electron is removed, so this one is removed. So Ar 3d5. Okay. Cu2 plus now is going to be Ar. So we're removing 2 electrons. So 1 from 4s1 and 1 from 3d5. So we'll end up with 3d4. So try for all of them. Try electronic configuration for all these atoms and ions, and then you can compare your answer. Pause the video, work it out, and then you compare your answer. Okay, so check your answers. Now you can write Ar, or you can write that in 4, which is 1s2, 2s2, 2p6. Okay, so you can write it in abbreviated form. Now the electronic structure and the periodic table. Okay, here there is a little change that you will need to do. So here it's the outer orbitals being filled. So let's see. So period 1, 2, 3, 4, 5, 6, 7. So when it is in period 1, we're filling in the 1s orbital. The outer orbitals that is being filled is 1s. Period 2, we fill in 2s and 2p as the outer orbitals. Period 3, 3s, 3p. Period 4, 4s, 4p. Okay, so depending on the period number, you know what orbital is being filled. Maximum number of so in the 4th period there is 3d, 4s and 4p. That's better. Now maximum number of electrons held in the outer orbitals, so 1s will hold 2, here it will hold 8, here it will hold 8, and here it will hold 6 plus 2 plus 10, that makes 18. So remember in your IGCSE, when you were writing electronic configuration, you would say that the first shell holds 8, first shell holds 2, second shell holds 8, third shell holds 8. So this is where it comes from. Okay, so number of elements in the first period, so there's 2 elements. Second period, you can count, you'll see there's 8 elements. Third period, you'll see there is 8 elements. Fourth period, you'll see there is 18 elements. What a coincidence. Now, relationship between group number and electronic configuration. So this is showing you relationship between period number and electronic configuration. Here, between group number and electronic configuration. So if it is found in a certain group, it will have the same number of valence electron in the outermost shell. So outermost shell will contain, so group 1 outermost shell will contain 1 electron. So normally here it will finish, so group 1 is in the S block. So group 1 will finish with something S1. Let's see lithium. Lithium is 1s2, 2s1. Sodium, 1s2, 2s2, 2p6, 3s1. potassium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, rubidium, I'm not going to write everything for rubidium. There is no need for you to write everything. So for rubidium, I'm going to shorten it and write so krypton, so 5s1. How do I know what number to put in here? So these numbers, how do I know what number to put in here? So this will depend on the period. So lithium is found in the second period. So let me put here period. So second period, here third period, here fourth period, here fifth period. So second period, here you have lithium. Okay, here you have sodium, here you have potassium, here you have rubidium. So depending on the period, you know what is going to be the number of the S subshell, the energy level that is going to be filled in. So group 1, so here you see here, so this is the valence electron. So if there is one electron, so it shows that it is in group 1. Okay, and the period number is going to tell us the energy level that is being filled in. So fifth energy level, so we're filling in the fifth period, we're filling in the fifth energy level. So fourth period, fourth energy level, third period, third energy level, and so on. Okay, so the period number will tell you what energy level to fill in, and the group number is going to tell you how many outermost electron there should be. Okay, so let's see for group 2 now. So if you look at this, so period 2, so you see we're filling in the second energy level. Period 3, third energy level. Period 4, fourth energy level. This is found in group 2, so the outermost electron we have 2. Okay, now group 3, so if it is in group 3, so you should have so group 2, it will end up with S2. Now group 3, it should contain 3 electrons in the outermost energy level. So 3 electron will be S2P1. So S2P1 consists of the outermost energy level. So here you see 2, 1, and again 2, 1. So it means they are in group 3. And then the period number is going to tell us which level you're filling in. So pretty easy, right? And then everything else inside is completely filled. All the orbitals inside are completely filled. So let's see for group 4 again. So second period, so we're filling in second energy level. Third period, so third energy level. This is in group 4, so it should end up with S2P2. So there's 4 electrons. You see, 2 plus 2, so that's 4 electrons. So here S2, so S2P2. Here. Now group 5, so it should end with S2P3, so that makes a total of 5 electron. So see here, 3 and 2, that adds up to 5. And then you have the period number that is going to tell you what energy level to fill in. So 3, so you see you're filling 3. 4th, you're filling the 4th. Everything else inside is completely filled. So here I've taken AR as the reference. Okay, so I'm not showing everything inside. So you can just write the noble gas and then everything that is going to be according to the period number and to the group number. So again, so you see period number 2, here it's 3, group 6, so there should be 6 outermost electrons, so that's S2P4, that makes 6. So you can see here everywhere it's 6, 2, 4, 2, 4, that makes a total of 6. Okay, so here this is the things in green. Whatever is in green, these are the valence electrons, and this is in the outermost energy level, and this is what tells you what's the valency. This is indicated by the group number. Okay, so complete for these ones as well, and then check your answers. So check your answers. So now you can see, so group 7 is going to end up with S2P5, so that makes a total of 7 electrons. Group 8 will end up with S2P6, that makes a total of 8 electron. Okay, and again the period number, so that's 2, that's 3, and that's 4 from the periodic. You get this from the periodic table. So 2, 3, and 4, you get this from the periodic table. So you can see we're filling in the corresponding energy level. Okay, so 2, here it's 3, here it's 4, so 2, 3, and 4. Okay, now for this one, note that I've put it in order of increasing energy level, but when I'm filling in according to the Aufbau principle. So I fill 1s2, 2s2, 2p6, 3s2, 3p6, then I'll fill 4s2, then 3d10, then 4p6. Okay, the order of filling in is different. So exceptions of all of this: electronic configuration of hydrogen, 1s1, it's not found in group 1, and it's not found in any group. And for helium, it's 1s2. Helium, it is not found in group 2, it's found in group 8 or in group 0. So these are the only 2 exceptions from this. Everything else you can get from the periodic from the periodic table. So from the period, so period 1, 2, 3, 4, 5, 6, 7. Okay, so you can see we're going to fill in according to the period number. Okay, right, so the energy level that you fill in depends on the period number, and also the group number here will tell you how many electrons there's going to be in the outermost level. So here there's 1, here there's 2, here it's 13, but it's group 3, 4, 5, 6, 7, and 8. Okay, so that's it. The video was really long, but there's everything in it, and you can work the questions now.